In this instructional video, we are going to work our assignment problems from Chapter 14, Lesson Number 2. You have been given a handout to save you the time from writing out the questions from our Chapter 14. So if you can find Chapter 14, Lesson 2, Rate Laws, Assignment 2 handout, you'll be all set to progress with my lesson. Now hopefully you've had a chance to try these on your own and you're using this video to check your work, and so it should go a little bit quicker if you have some of the things written down. But if not, if you're just getting to this video and your sheet is blank, feel free to pause and write things in as many as good notes as you possibly can to help you study the overall lesson. Let's begin with 14.22. It tells us we have a reaction A plus B forming a product C, and it's obeying the following rate law. Rate is equal to K, K is our rate law constant, times the concentration of A to the second power times the concentration of B. We call those powers the order for each reactant. It is second order with respect to A and first order with respect to B. Third order overall. And so let's begin by looking at letter A. If A, the concentration of A is doubled, what would happen to the rate? Of course, A is the second power, so if A is doubled, you can see what would happen. Doubling the concentration would make the reaction go 4 times faster. So the rate would increase by a factor of 4. What would happen to the rate constant? And don't let that bother you. You know, the word constant in math really is the same in chemistry. Constants do not change. The only thing that would affect a rate constant is changing the temperature. So rate constants do not change even though you're changing the concentrations of either the reactants. They remain constant, thus the term. We had said at the beginning that A is second order, and you see where I'm pulling that from. Raised to the second power means it's second order with respect to A, first order with respect to B, and I add the exponents to get the overall. So the overall is third order. The units for the rate constant in our notes we had talked about, I know they're going to be in a unit depending upon the overall order. So it's a concentration unit raised to some negative power, meaning that it's just a reciprocal value, and it's a time, and the most common time is in a per second. And always per seconds, because if you were looking at a rate law, what we're taking is the rate and dividing out the concentration to isolate K. Now, to get this particular number, the value here, the little trick is take the overall order and take it from the value of 1. 1 minus the overall order will tell us what concentration value to place here for my rate constant unit. So if we said the overall order was 3, 2 plus 1 is 3, 1 minus 3 gives me a net of negative 2. Molarity raised to the negative 2, second raised to the negative 1. And those negatives are just reminding us that they're reciprocal values. So sometimes you'll hear me say per second. Let's consider 24. Keep checking our work. An equation that has 2 NOs plus 2 H2s yielding N2 and water. The rate law for this reaction is first order with respect to hydrogen, so its exponent would be raised to the first power, and second order with respect to NO. Turn that into a rate law. Well, the rate law starts by saying the rate, remember the most common unit, a molarity per second, is equal to K, the rate constant, whose units are dependent upon the overall order, times the concentration of your first reactant, hydrogen, raised to the first power, times the concentration of the second reactant, raised to the second power. So first order with respect to hydrogen, second order with respect to NO, it would be third order overall. If the rate constant given to us at this particular temperature is 6 times 10 to the fourth, molarity raised to the -2, second raised to the -1. Now notice how that makes good sense for this unit. If the overall order is 3, 1 minus the overall order, 1 minus 3 tells me this -2 is a third order equation. We're given the concentrations of the two reactants. We know the rate law. We're going to solve for rate. So rate is equal to K. K was provided for us right here. 6.0 times 10 to the fourth power, molarity raised to the -2, second -1, times the concentration of hydrogen, who's right here, 0.015 molar, that's first order, times the concentration of O25, and that's to the second order, so we'll need to square that value. Hit that and see if we get a common answer. We have our rate constant, 6.0, raised to the fourth power, times 0.015, times 0.025 squared, and we get an answer. That answer I have is 0.5625. I'll just carry 2 decimals. So rate is equal to 0.56 molarity per second. What is the reaction at the same temperature? It's written there to let us know that the same temperature means that we have the same rate constant. When the concentration of NO is increased to 0.1, while the concentration of hydrogen is 0.01. So again, it's a matter of just plug and chug. We know the rate law, so we're solving for rate. Rate is equal to the rate constant, which is the same, but this time the hydrogen concentration is 0.01, and again that's first order, times the concentration of NO, who is 0.1, but he's second order. Let's solve for the rate this time. So hitting that same series, 6e to the fourth power times 0.01 times 0.1, but that needs to be squared because it's second order, and we get our value, which comes out to be 6, right on the button. So the rate is equal to 6 molarity per second. Going on to 27, the iodide ion reacts with hypochlorite, the active ingredient in bleach, in the following way. This is OI -1 and chloride -1. We see the data provided for us. We have what's called initial rate data. So what this means is we're able to calculate an initial rate by varying the concentrations over a series of 3 trials. So this experiment was conducted 3 times. In the first reaction, they had the same amount, same molarity of the 2 reactants, and recorded the initial rate. In the second trial, looks like they doubled the first reactant while keeping the second one constant and recorded the initial rate. In the last trial, they went back to the original concentration for the first ingredient, but then doubled the second ingredient and found the initial rate. We're to ask to find the rate law. How does varying the concentration of the reactants affect the overall rate? The easiest way to kind of get started here is, I know the rate law will start out by writing rate is equal to K, the rate law constant. We don't know that value yet, but we can calculate it in the next step once we know the rate law. I know it will be raised to the concentration of iodide, our first reactant. Oops, I grabbed this wrong. Oh well. I'm going to write them in reverse order, but that'll be fine. I negative came from this column, OCl came from this column. You may certainly have written them in the opposite order. But what we're trying to solve for is the power with which we raise those. So I negative raised to some power, OCl raised to some power, with which this data helps us figure out what order do these concentrations affect the overall rate. So the easiest thing I like to do is to find 2 trials that hold one of the ingredients constant, as in this trial 1 compared to trial 2. The reason I like that is now iodide is no longer affecting the rate. It is remaining constant. It's factoring out of how the rate changed. The only thing affecting the overall rate was changing OCl's concentration. When I compare from trial 2, 3.0 E negative 3 to 1.5 E negative 3, I see that that really is a factor of 2. Moving from trial 1 to trial 2 doubled the concentration, and you could see that easily. 1.5 to 3 is indeed doubling. What happened to the overall rate? Well, the larger 2.72 divided by 1.36, notice I'm just dropping the E negative 4 because that really is the same factor. And look what happened. It is directly 2. And so when I look here, this remained constant. Alrighty, so I'm factoring it out of my whole equation at the moment. When I doubled the concentration of OCl, the rate doubled. 2 raised to what power equal 2? 2 raised to the first power equal 2. We've just determined that OCl is first order. It doubled and had a direct relationship. That direct relationship is a first order. Let's suppose, and it wasn't, but let's suppose when I found this, if it had come out to a 4, then 2 raised to what power would give me 4? That's where we would find second order. So those are the two that we're really working for. Is it first order or is it second order? And friends, there really are many other possibilities, but at this beginning level, we're looking for first order or second order as our two choices. Let's figure out the last guy here. And what I'll do, I'm going to compare trial 1 with trial 3. And I'm going to do it this way because now this is constant and it's factoring out of the influence of the rate change. So holding OCl constant, I can eliminate it. It is not affecting the rate change. But I have the same kind of math going on here. When I compare trial 1 to trial 3, I doubled the concentration of iodide, and when I compare the rate from trial 1 to trial 3, it also doubled. Same value. So 2 raised to what power gives me 2? You got it. It's first order overall. Rate is equal to K times the concentration of I negative, first order, OCl negative, first order. There's our rate law, given a data table of initial rate data. Now I think the second part has us using that same data table, calculating the rate constant. So what I'll need to do is go back to that original table, and I'm just going to pull from trial 1 and insert into the rate law. So I could do trial 2 or trial 3. It absolutely doesn't matter because when I'm solving for K, it is a constant. Trial 1, 2, and 3 would give me the same value for K regardless. So this is where I'm going to pull. I'm just going to use trial 1 to find that information. So the rate is given. Remember our rate law, we just wrote it. Rate is equal to K times the concentration of OCl negative to the first power, I negative to the first power. Those could be in either order, you know that. And I'm just going to plug in what I know. Here's the rate, and here's the two concentrations. Let's solve for K. So the rate from line 1, 1.36 times 10 to the negative 4th molarity per second is equal to, K is what I'm solving for. Concentration of both reactants was identical, 1.5 times 10 to the negative 3rd power for both reactants. Solve for K. Here we have 1.36 E negative 4 divided by 1.5 E negative 3, and since it's the same number, we'll divide that, oops, I hit that wrong, E negative 3, and divide again by 1.5 E negative 3. I'm dividing out to isolate K. And when we isolate K, did you get a value of 60.44? If K equals 60.44, it does need to have a unit. 1 minus the overall order. The overall order is 2, isn't it? Because it's first order with respect to both reactants. 1 minus 2 gives me a concentration unit of molarity raised to the -1, and our overall order, second -1. So there's the rate. The K constant, 60.44, M -1, S -1. It's a second order overall. Let's calculate the rate. Now that we know the rate constant, we just calculated that, 60.44, M -1, S -1. But now the concentrations of these from a trial we never have to conduct. And that's the beauty of knowing the rate law. Once I know the rate constant by running just a few trials, I can figure out the velocity or the speed, the kinetics of a reaction by just inserting any values for those reactants. I'm not going to run this trial, but I can calculate the rate knowing the rate constant. So 60.44 times 2e -3 times 5e -4. We get a value of 6.04 times 10 to the -5th. And -5th, and that's a molarity per second unit. 6.04 times 10 to the -5th molarity per second. Same idea, yet another data table in number 29. We ran 5 different trials varying the concentrations of 2 reactants. We were able to measure the initial rate, and what we're trying to find out is the rate law. By varying the concentration, how did changing the concentrations affect the overall rate? So I can get started. Rate is equal to K times the concentration of BF3 raised to some power I don't know yet, times the concentration of NH3 raised to some power I don't know yet. But using the initial rate data, we're able to figure out with what order did BF3 affect the rate, and then again what order did ammonia affect the rate. Looking through your data, let's find some trials that hold one of the ingredients constant. Right off the bat, I can see this guy held constant between trial 1 and trial 2. And what happened here? Ammonia, and I'm going to read it backwards. I'm going to go from 2 to 1. I just like that. So I'm going from trial 2 compared to trial 1. That looks like it was doubled, wasn't it? So I can just show what I'm meaning. 0.25 divided by 0.125. Line 1 divided by line 2 gives me a factor of 2. Same here. 0.213 divided by 0.1065 gives me the same value. 2 raised to what power gives you 2? Well, of course, that's first order overall. So by doubling the concentration from 2 to 1, doubled the rate from trial 2 to 1, while the first ingredient was held constant, we now have figured out ammonia is first order overall. Let's examine the data table to find where ammonia is held constant and BF3 is changed. And we've got several examples. We could compare trial 3 and 4 or trial 4 and 5. Doesn't matter. Let's do 4 and 5 just because it's near the bottom. This is constant now. What happened to the concentration of BF3, trial 4 compared to trial 5? Well, I don't mean to be graphing. 0.35 divided by 0.175 is a factor of 2. I always just do bigger over smaller. My mind works better than that way than in decimals. So let's do the same way. Let's compare over here, trial 4 and trial 5. 0.1193 divided by 0.0596 gives me a factor of directly 2. So again, 2 raised to the first power is 2. These are both first order overall. The overall order of the reaction is simply 1 plus 1. It's second order overall. What is the value of the rate constant? You may use any trial. I just always use the first one for no other reason than it's written first. The rate in trial 1, 0.2130 molarity per second, is equal to the rate constant K, which is what we're solving for, times the concentration of our first ingredient, first order, times the second ingredient, 0.25, first order as well. So both concentrations were 0.25. Let's pull out K. 0.213 divided by 0.25 divided by 0.25 is 3.41. You want to say 3.41? Let's see, it's second order overall. 1 minus the overall order gives me molarity -1, and the time unit is S -1. Now that we know the rate constant, we're able to vary the concentrations of the reactants and calculate the speed without ever running it in the experiment. We want to know, what would the rate be if I've changed the concentrations to values we never ran up here? Well, now that I know the constant, 3.41, molarity -1, second -1, I can plug in those concentrations and calculate the rate. Since they're first order overall, we're going to simply multiply. And I'll just leave that in my calculator. 3.408 times 0.1 times 0.5, 0.1704. So we'll say 0.17. Molarity per second for my rate law, my unit there. Right? Good work. We have one more. It's our last problem in this assigned section, 14.32. Here we have a reaction to consider, and again, very similar. We want to find the rate law. Given 4 trials, we have 2 ingredients, both reactants, and seeing how they affect the overall initial rate. So we'll get started as we do by indicating that rate laws are written as rate equal K, the rate law constant, times the concentration of S2O8 -2, it's peroxy disulfate ion, raised to some power I don't know yet, times the concentration of iodide, raised to some power I don't know yet. Let's examine the data table and figure out those powers, the order with respect to each reactant. Can we find any trials that are held constant? Well, I'm noticing trial 1 and trial 2 hold this ingredient constant. I didn't spell that very well. Constant. So it will factor out. What happens here with the rate? All right, so let's see what happened to the concentration. I always do bigger over smaller, so 0.027 divided by 0.018. Okay, so the concentration factored 1.5. So the concentration changed by a factor of 1.5. Let's do the same here. 3.9. Since these are the same values, -6, I'm just going to drop them out. 3.9 divided by 2.6. That's also 1.5. 1.5 raised to what power gives you the same number back? Of course, that power is 1. It's first order with respect to S2O8 -2. What's interesting here is that I'm not finding a trial that actually keeps S2O8 the same. Notice how it's always varied? So, if that happens, that's okay. We just have a little extra math to do. So no time was this held constant. That was, in my mind, a poor experimental design, but let's do the math. Let's compare, and it doesn't matter, they're all changing, so let's do 3 and 4. Alrighty, so I'm going to just figure out how much each concentration changed. So I have 0.054 divided by 0.036. And that factors 1.5 again. Alrighty. Now this factor, 0.072 divided by 0.054 is 1.3. So I'm going to write that down. So that increased by a concentration factor of 1.3. Now what's happened to the rate? We're comparing trial 3 and 4. So the larger number, notice these are not the same values, so I'm going to include those times 10 to this. 1.4 e negative 5 divided by 7.8 e negative 6. And this is a factor of 1.795. But both reactants are influencing that speed. But here's what we know, that the concentration of S2O8 is first order. We determined that earlier, so it's directly affecting the rate. Let's factor out how much it's influencing the overall order. So by increasing the rate by that factor of 1.3, let me just check my math quick. Yeah, 1.333. And then this was indeed 1054 divided by 036. That was 1.5. So what we're finding is that they both have a direct relationship. Factor out one and it reminds you what the other is doing, and it's a direct correlation. So here, I'm just checking my math to be sure I'm illustrating correctly. Whoops, sorry. Yeah, so I have checked those math. Thank you for your patience. I just wanted to be sure we had those on, so about 1.8. What we've done is changed both concentrations, so we factor out how much is the S2O8 influence, and we were left directly with the 1.3, which was correlated perfectly. And this here essentially has to be the same number. So what I've done is factored out the S2O8 concentration so that it no longer is influencing the rate of change. These didn't work spot on, but you could clearly see 1.3 raised to some power gives you 1.2, and we all know experimental data is not necessarily 100% always exact, but you can clearly see that's very close to being the same number, so it'll be first order with respect to I negative. To calculate the rate constant, and it did say average rate constant, which would have us actually calculate for all 4 trials. And just to verify that a rate is indeed constant, here's what it asks us to do. From experiment 1, 2.6 times 10 to the negative 6th power is our rate, is equal to K, times the concentration of 0.018 raised to the first power, times the concentration of 0.036 raised to the first power. And those are molar units. Hitting for that, we get 2.6 e negative 6 divided by 0.018 divided by 0.036. And we get a value of 0.004. Let's see, it's second order overall, so 1 minus the overall per second. So trial 1 gives us a value of 0.004, molarity negative 1, second negative 1. What would trial 2 have given us? And I think I'll just hit that. So here's the rate constant from trial 1. So let's begin by hitting 3.9 e negative 6, divide out the concentrations of both reactants, and look, we get the same value, 0.004. So trial 2 also gave us the same number. How about trial 3? If the rate constant, 7.8, E negative 6, divide out the concentrations because they're both first order. It's a simple division. And we get 0.004. Whoops, negative 1, second negative 1. And just to verify, because the question asks us to, 1.4 E negative 5, divide out the concentrations, 0.0036. Remember, this one was kind of an outlier because we didn't get that exact match over here earlier. So it kind of makes sense to me. How about you? That this one would be a little bit off because that trial didn't necessarily give me accurate data. But I'll put it there. So the average, if I were to add up and divide by 4, clearly you're going to come very close to 0.004 as your average value. So let's use that rate constant, 0.004, to calculate the rate of disappearance. Oh, and we'll pull it down here. How is the rate of disappearance of the reactants related? So this is going to come back to lesson 1, where we talked about a rate expression. Alrighty, so that's the stoichiometry part. So remember, reactants disappear, that coefficient of 1 up here, the change in concentration of the first ingredient over a time interval is equal to 1/3 the change in concentration of iodide over a time interval. So that's just coming from the stoichiometry up above. And we could include the product side, but it didn't ask us to. It wanted us to relate the disappearance of both reactants. Now I want to highlight something. These rates were calculated by monitoring the S208. So these initial rates are giving us this particular value, right? The value here comes from here. So if the rate of disappearance is what we'd like to know of iodide when I know the concentrations, alrighty? So let's consider rate is equal to K times the concentration of our ingredients, S208 and I negative. Just repeating the rate law. Alrighty. What we're being asked to solve for, I just want to clear, when we were up here, rate is S208 negative 2. Alright, this is what we were calculating because that's what our temperature of disappearance was. So that's what we did here. But now all of a sudden we're comparing here. So the rate is equal to, now how are these two related? If I wanted to isolate this by itself, because that's what we're being asked to solve for, this is the rate that we're being asked to solve for, I could just simply put times 3 on both sides. Times 3 gets rid of the fraction of 1/3, and now I can have this. The rate of iodide would be 3 times the factor of K times the concentration of S208 negative 2 and I negative. So here's what we know. We want to calculate rate. The K constant, 0.004. S208, 0.015. I negative, 0.04. And when I calculate that, 7.2 times 10 to the negative 6 is my rate. 7.2 times 10 to the negative 6. And that unit is a molarity per second. When we solved earlier for the rates, we were given data for S208. Knowing that the stoichiometry plays a role in how we look at the how one reactant disappears with relationship to the other, I see that 1/3 of iodide gets consumed for every 1 mole of S208. So if I'm trying to isolate this rate, I need to get rid of that fraction. That is why the 3 is appearing here. 3 times this value, isolates this concentration, and we're able to solve for its rate, 7.2 times 10 to the negative 6th. And you've just earned your A+ on Lesson 2.